All right, run number 2. How do you use a sampling distribution with StatKey for proportions? We saw it for the mean in the last video. If you do this for a proportion, they're telling you you have a proportion over here. If you haven't watched the mean one, you might go back to watch the sampling distribution mean video. This represents the population's proportion. So it is called a parameter because it came from the population. Notationally, the proportion from the population is little p. So little p is equal to 0.275. As a percent, that's like 27.5% if you move the decimal. What do we want to do? We want to choose how big of a sample we want. We'll take a sample using that proportion that's randomly generated, and then we'll go plot it. So here we've got 200. We generate one sample. The sample that we got, out of the 200, 46 of them were considered successes. 46 divided by 200 is a proportion of 0.23. What is this? This is a sampling proportion. The sample's proportion that we generated is P with the little hat. It is a statistic. So the proportion at the top is for the population. Because it's the population, it's called the parameter or a parameter. If you get one of these from a sample, it's called a statistic. Notation, the populations was P, the samples is P hat. We go and plot the P hat value down here. This big graph is called the sampling distribution. We want to go generate a new sample of 200. This new sample gets 68 out of 200. It generates a new P hat. We plot the new P hat here. We go back and do another one. We get a new P hat and plot it here. This little arrow is pointing to the average mean proportion of the 3 that we've plotted. If we keep on doing this a bunch of times, we see something very similar to what happened with the mean that we played with in the last video. What's going on? If you do a ton of samples, you see this distribution and it's centered at 0.275. We have a standard error up here. That represents the standard deviation for this graph that we just made, called the sampling distribution. And what we like is the mean for this graph, as long as we generated a bunch of samples, is always going to be equal to the population's value. So ours is centered at 0.275, which happens to be a great estimate for what our population was if we hadn't known it from the get-go. So the idea with this is if we take enough samples, the center of the sampling distribution for all the samples we took would be centered at the bottom, and that center is a great estimate for the population should we not know what the population's actual value is. As we get the n value up here bigger for every sample created, the standard error value will get smaller, making the scale on the bottom of our graph narrower, which makes our estimate for the population value down here much more accurate. Hopefully this will give you an idea for any problems you face that involve this kind of generating a sampling distribution using some type of software. I'll try to post some more videos here in the future. Hope this one helped you out. Take care. Bye-bye.